Anyway, okay, so so this talk is sort of well, it was meant to be a follow-up to what Michael said, but I think he didn't say it really. So I hoped he would save me my introduction, but that won't be the case. So this is about an attempt to estimate how fast waves can be generated by slow flows. When the flows are really slow, then those waves have really small amplitude, and so it's an attempt of sort of going beyond this limit, although I'll come back very often to the limit of slow flows because I find it interesting. Okay, so just a brief introduction about things which most of you already know. That the atmosphere and ocean are dominated by large-scale slow motion, which is balanced in the sense of being near hydrostatic and geostrophic balance. However, there can be fast motion, imbalanced motion, which we can just describe as inertia-gravity waves, although that may be something else, maybe fast instabilities, for instance. Okay, and as we know, the Rossby number, which I will call epsilon, estimates the timescale separation between the slow motion and the fast motion. Okay? So inertia-gravity waves have typically not everywhere small amplitudes, but people care about them, for instance, if they care about the mid-atmospheric circulation, if they care about small-scale mixing, and maybe if they care about dissipation of the large-scale motion, which, as we've seen in Jim's talk, well, has difficulties dissipating if there is no fast motion involved. Okay, so the problem I'm going to focus on is the business of spontaneous generation of fast motion. So the question is, how can motion, which is initially slow, just by its dynamical evolution, generate fast motion? So without any forcing, without any sort of initial imbalance, for instance. So it's a question which has a long history, which is best summarized as the question of whether there exists an exactly invariant slow manifold, which I think is now understood to not to be the case. So slow manifolds can be defined, but there is always some sort of fast motion around them, which Michael describes as this fuzzy or quasi-manifold. And so here are some of the names of people involved: Lorentz, Michael, Tom Worm, and Rupert Ford. In recent years, the subject has been sort of revived, I think partly because people have started to simulate those gravity waves. Well, just observe them in simulations, really. And just I want to show two examples. So this one is from simulation by Ploegoven and Snyder. What they've done is simulate Barclinic instability in a rather standard fashion, but diagnose the fact that even though it's a slowly evolving Barclinic flow, Barclinically unstable flow, some gravity waves do appear. So if you just can see those three panels, 1, 2, 3, they show horizontal sections. The arrows are the velocity field. There is one potential vorticity contour, and then the gray, the shading areas correspond to the divergence field. Okay, so what you see is that as Barclinic instability develops, so you have those meanders being created and increasing in size, the divergence shows the signs of well, gravity waves, so those bands of sort of upward and downward motion, if you like. Okay, and so that can be diagnosed as being gravity waves appearing spontaneously in those situations. And another example I wanted to show, because Eric Dagnew is now in Edinburgh, so and also because it's an oceanic example. So this is from very high resolution simulation of an ocean driven by Barclinic instability. And this is a section of this field is the vertical velocity at some depth, at 2,000 meters or something. So what you see is that a bunch of vortices which are shown in the vertical velocity, but if you look close, I'm not sure you can make those out, but you can see also bands of strong and very large and very small divergence, making sort of parallel stripes characteristic of gravity waves. Okay, you see some here, some here. Okay, so these are simulations which were not designed to capture gravity waves. They just happen to be there because of the extremely high resolution of those simulations. Okay, so my interest is more in the kind of analytical ways of capturing this gravity wave emission. And on that side, there are sort of two regimes which can be studied. The first one is the one Michael alluded to, and it's the regime of light irradiation, which corresponds to having very small full numbers. The idea there is that if you have a small full number but no significant rotation, gravity waves can be slow if they have large enough, a scale which is large enough. Okay? And then you have some emission of gravity waves through a resonant process where the slow motion excites very long gravity waves whose frequency is matching the frequency of the slow motion. And then the other regime, which is the one I've been most interested in, is the one of small Rossby number. In that case, there is no overlap between the frequency of the gravity waves and the kind of frequencies of the flow because of the lower bound of the frequency given by the Coriolis parameter. And in that case, you can argue and show in some cases that whatever gravity waves will appear will be exponentially small in a small parameter, okay, of this form. So formally smaller than any power of the Rossby number. Now, the observations of simulations I've just shown will confirm that you really need Rossby numbers of order 1 to see substantial gravity waves appearing. And also they suggest that those waves have rather small scales compared to the scale of the typical eddies, which you see in this flow. Okay, so what I want to propose here is an approach to then study those waves without relying on the smallness of epsilon, because, well, essentially, where the waves will be substantial then or significant, then this Rossby number will not be small, but relying instead of a spatial scale separation. So the fact that the waves have a much smaller scale, spatial scale than the background flow, if you like. Okay, so the idea is then in the usual way to do some sort of geometric optics approximation. So the idea here is really to think of a background flow as being a balanced flow, which can be quasi-geostrophic or any sort of balanced flow you can think of, which is complicated, time-dependent, turbulent maybe. Add a little perturbation and see whether this perturbation can grow as a gravity wave. Okay, so the perturbation is written in this form where you have this rapidly varying phase factor telling you about the fact that it's a small scale perturbation. So in the usual way, the wave vector will be the gradient of the phase. The frequency will be the time derivative of this phase. And if you just blindly plug that into the Boussinesq equations, for instance, what you find at the first order, the leading order in the small parameter, so my mu here is the spatial scale separation parameter. What you find is that the frequency is just given by the Doppler shift term. Okay, so I mean it's what falls off. And then at the same order, I suppose, you get an evolution equation for the wave vector, which is the usual one for a wave whose frequency is just Doppler shift term. So it says that the wave vector is going to be evolving according to the deformation field, the strain field.
And assuming zero intrinsic frequencies, you apply that?
Well, so I'm not assuming anything. I'm just saying that the waves have very small scales. Okay, and then if the scales
equals u dot k.
Yeah, right. So I mean, what is happening is that if you assume that the waves have really large k, very small scales, then this term dominates the intrinsic frequency. Okay, so that's the regime of wave capture where the group velocity is just advection by the background flow. Okay. So this somehow, I mean, it looks a bit unusual in the sense that one is used to seeing the intrinsic frequency beside the Doppler shift. But in fact, it was false naturally in the case of stratified flows, simply because their intrinsic frequency, if the aspect ratio of the wave, so if the ratio vertical to horizontal wave number is of order 1, then as you increase the magnitude of the wave vector, the Doppler shift always dominates compared to the intrinsic frequency, which remains of order 1. Right? So it's very different from what's happening for shallow water, where as you increase the wave number, the intrinsic frequency goes to infinity as well. Okay. And so final remark is what I'm just talking about is essentially what other people have developed, first for unstratified flows and then for various variations on that to study stability. So that's what's called the geometric optics approach to stability. And those people tend to use this rather as a means of proving instability of some flows than a kind of practical diagnostic tool, which is what I'm proposing. Okay, so far I've just kind of rediscovered the kinematics of waves. Then what is happening at the next order is that you should get amplitude equations governing the amplitude of your wave, right? So here are my amplitudes. They will depend on the, I'm following a wave packet. And so as this wave packet evolves, its amplitude will change. Now in the regime I'm at, wave action conservation goes down the drain, really. It doesn't hold because I'm making no assumption about frequency separation. Okay, so I have to keep essentially 3 ODEs governing the amplitude of these waves. And one way of writing those ODEs is in terms of the potential vorticity of the little wave packet I'm following. So I'm not ruling out the fact that this wave packet is not only a gravity wave, it can be also a little wave packet of potential vorticity. The second useful component is the vertical component of the vorticity and the divergence. Okay, so I just show those equations very briefly. So what there is to be seen is that it's a coupled system of three ODEs. If you just look at divergence and vertical velocity, what you recognize here, okay, it's an oscillator. This alpha is essentially 1. It's an oscillator, and here is the frequency of the gravity waves. Now this frequency is going to change in time because the wave vector is going to change in time. And then there are some corrections depending on the flow, and I've kind of scaled things. Well, I've put it in front of sort of bookkeeping parameter epsilon, which tells me which parts are going to be small when the flow is slow. Okay, so I mean, all this thing will be important in general, but can be neglected when epsilon goes to 0.
What is dot?
What is dot? Dot means time derivative following the wave packet, which means following particles, if you like, because the group velocity is the flow velocity. Okay, so these are 3 equations for amplitudes. They have to be solved coupled to, well, the equation for the wave packet position. Again, the epsilon here is just a bookkeeping parameter, and the equation for the wave vector. Okay, so in principle, it's a set of, I guess, 9 equations. Yep. Except that I've assumed, I think, that the vertical velocity of the background flow was negligible. Okay, so if you now say there is no flow, well, then the wave vector remains constant, and you rediscover the existence of waves, right? The solutions are just oscillatory in time. One solution has 0 frequency, kind of vertical mode, and then you have those 2 gravity waves, okay? But in general, I'm going to be interested in having some flow. In that case, the flow will affect the dynamics in 2 ways. So first, the fact that the wave vector becomes time dependent, and that depends on the strain. And then also, as you've seen in the equations before, there are also a bunch of terms which are there because of the presence of the flow, and they're also entirely given by the strain field. Okay, so if you know the velocity field and the strain field, you know all you need to know about this, about the dynamics. Okay, so the equations look a bit sort of complicated. We can just summarize the behavior by saying that they look like this, right? So what you have is an oscillator for whichever amplitude you want to look at, oscillating at the inertia-gravity-wave frequency. It's an oscillator which might be forced if there is some potential vorticity in your little wave packet. And then it contains also correction terms of well, orders which are small if the flow is slow enough, okay? So in the case of slow flow, you have a linear oscillator with slowly varying frequency. Now this is a kind of toy model for balance dynamics, if you like, or for the issue of waves generated by balance dynamics, because when you look at this equation, you can do balance if you like. So balance is saying, well, let's start with initial conditions with no gravity waves. And then let's assume that the evolution is slow, which means essentially let's drop the time derivative here and let's drop epsilon terms there. Okay, so for instance, the leading order balance model, we say, well, to balance my flow, I need to start with a divergence given just by whatever those terms are times the PV divided by the square of the frequency. Okay, and you can do order by order, you can do balance in that way. And so what you find is that in this toy model, as in the kind of the real PDEs, all your fields, in particular this vertical velocity, will remain balanced to all order in epsilon if it's a small parameter. Okay, so you will never find any gravity waves being created at any power of the small parameter. What you can do, however, is do some sort of WKB approach in time now to try to capture whatever fast oscillations will be generated in this slowly varying oscillator. Okay, and then well, you realize that those oscillations are switched on by a Stokes phenomenon, so this kind of asymptotic phenomenon, and the amplitudes are exponentially small in epsilon. Okay, so the model allows to kind of differentiate two ways of generating gravity waves. One is when you start with some non-zero potential vorticity to your little wave packet, so you have a bit of a vertical mode. And then in the course of the evolution, because of the time dependence, this vertical mode is going to give some of its energy to inertia gravity waves. Okay, it's a kind of conversion mechanism, well, a bit like conversion in sort of WQB approaches, standard WQB approaches. And then the other mechanism is one where you start with no vertical mode. You start with just a very small initial perturbation in the form of gravity wave, but this perturbation is amplified by some instability mechanism. Okay, so in this model, one can sort of distinguish those two processes rather clearly. In more complicated setups, it's sometimes less clear. Okay, so let me illustrate the two types of mechanism by essentially recycling all the results, because I'm describing an approach which is local, where you say I just need to know the flow along one particular trajectory. But if the flow happened to be everywhere of that form, then the results can apply. So something which had been studied before by Jim McWilliams and myself is the case of just a Couette flow in the horizontal, just a linear shear flow. Now I can say, well, if I have a flow which is locally like a shear flow, what is happening to my little wave packet? And then the answer is that if you start with some vertical mode, you let it be sheared by this shear flow. So what that means is that the phase lines of your wave packets are going to be tilted by the shear. And then some gravity waves will be generated precisely when the wave vector is parallel to the flow, which means that the phase lines are perpendicular to the flow. And so here's just a little illustration of this, where so I'm showing the vertical component of vorticity as a function of time, and the evolution is a smooth balance type of evolution followed by some oscillations showing gravity waves which have appeared. Okay, now I want to illustrate instability mechanisms. So what can happen when the potential vorticity is initially zero? So you start with a wave packet which is just a little gravity wave packet with very small amplitude, and you watch it being amplified by an instability. So the simplest model here, well, a simple model is that of elliptic instability. So if you have a flow which is locally elliptic, so streamlines are elliptic and vorticity is constant, you can just study those three equations, which has been done, well, essentially before by Miyazaki and then McWilliams and Yavne. Because it's a periodic, well, it's a closed streamline, the wave vector is going to be periodic in time. And so the equation for my equations, if you like, reduced can be reduced to a second order differential equation with periodic coefficients. And then it's no surprise that growth is possible through parametric resonance. Okay, so in the system you have three parameters. So one is the Rossby number, okay, which tells you about the strength of the flow compared to the Coriolis parameter. Another parameter is the eccentricity of the ellipse. And the third one is a kind of Berger number, which gives you the aspect ratio of the wave you put in the system, well, measured in kind of natural coordinates. Okay, and so what's happening in this setup is that there is indeed a parametric instability, but as you increase rotation or you decrease the Rossby number, the order of the resonance which leads to this instability is getting higher and higher. Okay, so you have to deal with a resonance of order going to infinity as the small parameter goes to zero. this can be nonetheless handled. So I've done that recently with a student of mine, Jonathan Asbden, and so you can calculate the growth rate of this elliptic instability in the limit of epsilon going to 0. And in the, what is now for me the usual way, and this is exponentially small in the Rossby number, so there's a parameter alpha which can be calculated, and a parameter beta, and so the growth rate scales in exactly this way. Okay? And one question which was interesting is the difference between cyclones and anticyclones, because I think numerically cyclones seem so stable, if you like, that the instability hadn't quite been spotted. Well, in fact, the difference between the two situations is that the growth rate differ by a factor of order 1, which is this exponential beta. But as you can see, I mean, so this sigma here is 1 for anticyclones, so it means the growth rate of anticyclones is larger than the growth rate of cyclones by an order 1 factor, which happens to be rather 100 or something, which means that the instability of cyclones is really, really weak. Okay. So here's just an example of the kind of result that you get. So I'm showing here for fixed eccentricity and, say, Berger number, the growth rate of this elliptic instability as a function of the inverse of the Rossby number, so rotation increases this way. And so you get those typical bands, very narrow bands of instabilities, obtained numerically, and then the asymptotics matches that pretty well. So this is the case of an anticyclone, and if you look at the cyclone, somehow it's not quite the same parameters, but the growth rates tend to be, what is it, well, 1 order, or in fact probably 2 orders of magnitude smaller. Okay. Right, that's about what I wanted to say about this. So one can play.
4 minutes.
Okay, so one can play various games in very simple flows. For instance, point vortices. But I won't discuss this obviously now. Something I want to discuss is what you get if you think about the flow as about the random strain model of the flow. So everything is controlled by the strain field of this flow as seen by a particle moving with the flow. So a good idea is to model this as a random process of some sort. It's a good idea, for instance, studies of passive scalar advection have shown it's a good idea. In that case, the magnitude of the wave number increases exponentially, but this magnitude is irrelevant to the business here, because what counts is the frequency of the gravity wave as seen on this wave packet, and this frequency depends only on the angle of the wave vector. So this frequency tends to a stationary random process. Okay, so even though the length of the wave vector is going to increase, the frequency of the corresponding gravity wave is going just to randomly fluctuate. And so if essentially amorally the system that you get is of this form, where this is a stationary random process, well then, well, it's well known, I guess, that these sort of equations have solutions which increase exponentially in time, and the growth rate here is the Lyapunov exponent. Okay, so you're left with finding the Lyapunov exponent for a randomly, for an oscillator with random frequency. Okay, and so there's a theory for that used in, well, the people from the program, the kind of companion program working on Anderson localization must know those things very well, because this is one of the key results, is how to find the Lyapunov exponent given frequency fluctuations. And so, I mean, things here are a bit complicated, but roughly speaking, what's happening is that the Lyapunov exponent, so the growth rate of your perturbation, is given by something which is essentially the correlation function. So it's essentially the frequency spectrum of the frequency evaluated at the high frequency of the gravity waves, if you like. Okay, so this type of argument tells you that this growth rate will be highly sensitive to the smoothness of the frequency, and sort of equivalently the smoothness of the strain field as observed on a particle moving with the flow. Okay, why the smoothness? Well, because those frequency spectra decay like power laws if the frequency, so this is a frequency spectrum of the frequency, right? It's slightly confusing. So if this function of time here is differentiable n times, then you can expect a decay, like some sort of power of a small parameter, if this frequency is a very smooth function of time, real analytic, then you can expect this power spectrum to decay exponentially, okay, which says that the growth rate of your wave packet is exponentially small in the Rossby number again. So something I thought I should ask, since I've here experts on turbulence, it's a very simple question, I think, which is, if you sit on a particle in a turbulent flow, turbulent as in geostrophic turbulence, what will be the frequency spectrum of maybe the inertia-gravity-wave frequency, or even more simply, the frequency spectrum of the strain field. Okay, so I'd like to know whether this frequency spectrum decays like some power law, and then which power law, or whether it's exponential, which is not to be ruled out because the strain field is dominated by the large-scale component. Yep, that's exactly it. Okay, so just my conclusions that I've just described an approach to study the wave generation in flows which can be very complicated. And so the idea is to let go the frequency separation, but just keep the time scale, the spatial scale separation. In that case, you're left with following a wave packet which moves with the flow, a wave vector which changes the function of the strain in the flow, and then 3 amplitude equations, which I've shown. And so this leads to a kind of toy model, if you like, where you can distinguish mechanisms of growth of gravity wave energy. So either you kind of transform vortical mode into gravity wave-like mode, or you have instabilities where the gravity waves kind of manage to grow by themselves. Okay. Right at the moment, what we're doing is trying to kind of use this as a diagnostic of semi-realistic flows. So the simulations obtained by Riwal-Plougonven of Barclay instabilities. And then there are other games you may want to think about, which is to think about what is happening when you are in a kind of more traditional WKB setup where there is an intrinsic frequency. And in that case, life is much more complicated because the various branches of your dispersion relation will travel at their own group velocity. So there will be a kind of spatial decoupling between the 2 branches of the gravity modes and the vortical mode. Okay, I'll stop there.
Go back one slide. And if what's important is to characterize the space-time structure of the strain.
The Lagrangian structure, so the Lagrangian frequency spectrum of the strain, or even better, of the frequency of the gravity waves, which follow from this strain.
And you're making a distinction in terms of how differentiable it is. Other people might make characterizations of the spectrum or higher moments. What is the relevant measure to fit into this kind of growth framework?
Well, so the relevant measure is that you should look at
all the results cited for Gaussian. The results he cited was for Gaussian statistics.
Well, but I think for the, yeah.
Fine, we know we have non-Gaussian strain. So where does that take?
Well, I think for the high frequency thing, certainly for rough enough. I mean, this kind of result can be obtained in a very simple way, actually, just by semi-rigorous analysis. Okay, which
Gaussian statistics.
I don't think that's the case, actually. But certainly, I mean, if the noise is kind of rough enough, then you don't need Gaussian statistics, I believe. Anyway, so to answer your question, I think what needs to be known is, if you look at the frequency spectrum of, say, the strain as seen by a particle, then the issue is what is the tail of the frequency spectrum? Okay, and so what is the power that you have at the inertia-gravity-wave frequency?
I'm trying to pull out of this there must be some sort of competition between these elliptic type instabilities and other spontaneous growth of waves and the wave capture process that tends to kill them, which I was going to advertise as the third mechanism to stay close to balance, by the way. But actually there's some competition according to this analysis. Which one do you see winning?
Well, what do you mean kill them? I mean, so even in a pure strain, some of the fields will actually increase, right? Like the divergence associated with your little wave packet will increase as this wave packet is being strained by
But of
pure
course, you
strain.
expect the wave to break then.
Well, that's
because
right, yeah.
Local amplitude is, so it is rather strongly dissipative. And that's the competition between that and the spontaneous generation in the elliptic flows, for instance.
Right. So, I'm not sure whether there's a question or not. I mean,
Well, I'm just wondering which wins. You see, I was going to argue that wave capture
suppose-
is more powerful and that it will tend to get the flow back closer to balance by destroying the gravity waves.
well, I mean, they need to grow from somewhere, I suppose, right? So if you have a flow which is rather jerky, but without much strain, perhaps, then you can generate gravity waves, and then these will be then strained and dissipate.
Okay, that's why I think the dipole example is important, because it's clear that the wave source is non-WKB. It has the scale of the whole vortex.
Right.
Only when the waves get away and become captured do they become WKB.
Yeah, I mean, here it's a bit of an artificial assumption, I suppose. But the point is, I think there is no alternative, really, to study those things, except for by looking at simulations.
Break in and try to use gold afterwards.